I lost my connection. What happened? There we go. Okay. The one set of questions at the end where it asks you to use a calculator to evaluate each function and then round your answers to the 4 decimal places. We're going to talk about this more when we get back. But when we talk about angle measures and then taking the sine or cosine or tangent or whatever of that angle measure, there's actually more than one way to talk about angle measurement. So the way we're most familiar with at this point is in terms of degrees, how many degrees an angle has. But there's also a measurement called radians. Now you may have heard of those before, you may not have heard of those very much before, and that's okay. We'll talk about those more when we get back after break. But what I want to point out to you is how do you make sure your calculator is doing what you want it to? Because what type of angle measurement you're using makes a big difference in what kind of answer you get. Okay? So just really quick here, I want to show you where you set that, in case you're not aware. So when you are on your home here, what the heck? There we go. A little lag. You've got this settings choice, which is number 5. Okay. And then you have lots of different options, and what we're interested in is the document settings. And then right here is where you change things. Okay, so right now my angle setting is set for radians, but we're not using radians right now. We're using degrees mostly. So I need to change here to degrees. And then what I would suggest you do is down here where it says make default, hit that instead of just the OK. There's something about just hitting OK that doesn't always apply to everything. So if you hit the make default, then it will apply to anything that's open. And the next time you come back, it will be in degree. It'll stay in the degree setting until you change it again. Okay? And it'll ask you if you want to apply it to everything. So you just say yes. And so then when I come back up here to the calculate scratch pad or to a new document, I hope you all found the Trig button is over here underneath the blue control button. And the nice thing is when you click on that Trig, you get all 6 of them. Back in the old days of the TI-84s and some of the older calculators, you would only get sine, cosine, and tangent as buttons to use. And then if you wanted the cosecant, the secant, or the cotangent, you would have to find like sine and then take 1 over sine to get cosecant. You would have to get the cosecant yourself. But the TI Inspires actually have all 6 of them there ready for you to use. So you just pick the one you want. If we want sine, we pick that one. We put in our 16.35 now. And it's going to know that I mean 16.35 degrees because I've changed it to degrees in the settings. So when I hit enter, I get my answer. Okay. Now the other thing that you can do, if you're not sure how your calculator is set, or for some reason you've mostly been working with radians, but you just have these 1 or 2 problems where you just have to work with degrees really quick, you can also go in and say, all right, I want to do cosine here, and I want to do cosine of 57 degrees. But I don't want to go to the settings and change out of, I just want to do a quick problem. So I can do my 57 here, and then I think it's this one. See the pi symbol down here beside H? If you click on that, you get a menu of a bunch of different things you can use, and one of the things is the degree sign. So if I put that degree in there, even though I may have my calculator in radian mode, putting the degree symbol overrides that, and it will calculate this now as 57 degrees. So that's another thing you can do if you're either not sure, or you know you're in radians, but you don't want to change it all out because most of your problems are in radians right now and whatever. Nope. Just use your actual, okay, just use your actual degree sign. Now look at the answer that it gave us. Is that helpful? Not really. The reason for that is something we'll get to actually in the next chapter. But what do I do when I get that as an answer? It's like, okay, how am I supposed to get 4 decimal places out of that, or whatever it is I'm supposed to get? Like, what the heck? Well, the reason we're getting this is because I think right now my calculator is set to be in exact mode. And so in order to get a decimal answer, I just need to go Control Enter. Okay, because you'll notice above the Enter button, there's that little squiggly equal sign, the approximately equal to sign. And so what that means is that in order to get the approximate answer, I have to go Control Enter, right? Because it's in the blue. And so if I do Control Enter, it will then give me the approximate decimal answer rather than the exact answer in terms of sign. So when that happens to you, if you punch something in and then you get some weird answer like this that doesn't really mean anything, just go Control Enter and it will take that previous answer and give you the decimal version of it. Okay? All right, so just a couple of quick things about the calculator. The number 9, A, B, and C, where we have those strange fractions with the pi's in them, those are examples of radian measures. Okay? Now, if you didn't quite get those this time around, that's okay. Like I said, we'll talk about them more when we come back from break. What actually happened there, and the reason I'm not too concerned about it, is because compared to what I did last year, I changed my first 2 lessons around. So what we're doing as our first lesson this year was actually my second lesson last year. So we'd already talked about degrees and radians when we got to this lesson, and I forgot about that. So when I switched the order around because I felt it fit better this year, I forgot that I had those couple of radian ones in there. So if you knew it and you figured it out, great. If not, don't fret. We'll get to it when we come back from break and you'll understand what's going on later. Okay? Everything else I think was mostly radians. 11, you had, mostly degrees. In 11 you had radians, but since it's all about the calculator, you just punch what you have there into the calculator and it'll give it to you. But then that's when you have to change back to radians again. When you have those pi's in fractions, that's a pretty good indication that you're talking about a radian measure. So your calculator would have to be in radian mode to figure those 2 out. Okay, so you'd have to switch back and forth. What about 12? If you're going to do 12 on your calculator, should you be in degree mode or radian mode? What do you think? Even though you don't really know what radians are, by looking at what is written for parts A and B in number 12, do you think that my calculator should be in degree mode or radian mode? And to be honest with you, I'm not sure I did that right. I'm not sure I have 11. Okay, we're going to redo these really quick. because I have to be honest, I was really tired when I did these answers last night, and I don't think I actually changed my calculator, so let's just double check them really quick. Number 11, we need radians. Now, one of the nice things is, if you have done a recent update of your computer or your calculator software, one of the new things that Inspire has done is given us this little indication up here. What's going on today? Up here in the corner by our battery symbol of whether we're in degrees or radians, so that you know. If you're not seeing that on your calculator, then that means you don't have the latest update of your calculator, and you can go onto the TI website and get it. It's free. Just download it, get it onto your calculator. So right now, on mine, I can see that I'm in degree mode. So I'm going to go back. Not menu, home, settings, document settings, change this back to radians, make it the default. Yes, okay. Please catch up with me. There we go. All right, go back to my calculate. So in number 11, I need the cotangent. So trig, cotangent. I need pi over 16. Pi is in the pi button, thankfully. So pi divided by 16. Hit enter. There's one of those funky answers again. So now I'll go back and do control enter. And yes, that is incorrect. I thought that was weird when I was doing it, but I was so tired I couldn't get my brain to figure it out. So 5.0273 is the correct answer to 11A, to 4 places. 11B, 11B, trig, we're doing tangent. Now, actually I have two options here. I can go and do tangent, type in pi over 16 again, or, what do we know about tangents and cotangents? From last class? They're what? They're, yeah, inverse, reciprocals of each other. So I could also just take this answer that I got from cotangent and do the inverse. 1 divided by my previous answer. That's what my tangent would have to be. So that should be a 0.1989. Okay, so those should be the two answers to number 11. Go ahead and fix those quick. Sorry about that. All right, so now to my question about 12. Should I stay in radian form, or should I change it back to degree form? And what's the indicator that tells you I should stay in radian? There's no degree symbol. Yep. So most of the time radians are going to look like what you see in 11 with those pi signs in them, and they're going to be set up usually in fractions and things like that. But they don't always. Sometimes radians are just plain old decimals like other numbers. And so how do I know then whether I'm talking about degrees like I am in number 10 or radians like we are in 12? It's all about the degree sign. Okay, the degree sign in number 10 tells me we're talking about degree angles. But not having the degree sign in number 12 tells me that these are actually radians. So I'm going to stay in my radian form. I'm going to go to trig and pick secant for the first one. Yep, secant. 0.75. Enter. We got 1.3667. Sounds better. 1.3667. for secant. And then cosine, again, I could either go up here to my trig and find cosine, or what's the relationship between secant and cosine? What? What do you know about secants and cosines? They're what? They're the inverses also. So secants and cosines are reciprocals of each other. Sines and cosecants are reciprocals of each other. Tangents and cotangents are. So I can either go up here and just do the cosine of 0.75, or I can do 1 divided by the answer I got from the secant. And so that one should be a 0.7317 if we round it correctly. Now, that should not affect the quiz that you did, because the quiz, I asked you for 10 and 10s in degrees, and I did that one right, I think. But just for the sake of having the correct answers, make sure you get 11 and 12 corrected.
Wait, so that 12A is 0.7?
12B is the 0.73. 12A is the 1.3667. Okay? All right. So today we want to extend our understanding of how to work with right triangles to things that are a little bit more real life oriented. So if you look at your 2.1b notes page, you see 2 word problems there that we're going to take a little time to work on. And then again, my goal for today is to make sure we give you enough time that you can work on the 2.1b practice before you leave, and hopefully get done with those problems so that you don't have them hanging over your head over the interim and break. And then the only thing you're really responsible for over break is memorizing those special angle trig values. Okay? All right, so at this point we should be able to close our lids and let's talk about how we use right triangle trig for some application kinds of problems. Okay. All right, so the first problem says that a surveyor is standing 115 feet from the base of the Washington Monument as shown in the figure. Okay, you can probably see a little better on your paper than what you can up here, but you're seeing the same thing. So this is meant to be the monument, and our picture got a little light up there. So the monument looks something like that. If you've been in Washington, D.C., you've seen it. Okay, and our surveyor here is this tiny little person right there. So he's 115 feet away from the base. And they've got that marked on our picture and measured off for us already. Okay? Says the surveyor measures the angle of elevation to the top of the monument as 78.3 degrees. So when he looks up from where he is down here, he's determined that the angle right here that's being made from the ground as the bottom, and then his line of sight looking up to the top of our monument here, that angle is meant to be the 78.3 degrees. Okay? Because he is looking up, we call that an angle of elevation. So you see this kind of terminology quite a bit in trig problems. An angle of elevation or an angle of depression. Okay. So when we talk about this, what we're really saying is if someone is looking straight out, Okay? We're assuming that that line of sight is parallel to our ground. Okay? If we look up from there, then we have an angle of elevation. And the angle is measured from whatever parallel to the ground would be. Okay? So looking straight out parallel to the ground is our starting place. If I look up from there, then the angle of elevation is the angle that's being made between my new line of sight looking up and that original line of sight that was parallel to the ground. Make sense? Whereas if I look down at something, then the angle that's being made here is what we call the angle of depression. Okay? So when you see that kind of language in a problem, you just need to recognize what it means. It just means that from straight line of sight, angle of elevation meant he looked up to see the top of the monument. Now, how do you get an angle figured out from that? Well, there are fancy devices that will measure that for you. So if you're like actually into surveying as a profession, you probably have a pretty fancy little tool that will allow you to set this as parallel, and then as you move up, it has mechanisms in it that can measure how much you've moved it and tell you what that angle is. But there's also really simple ways to do that. And I'm hoping that we can get through these two problems pretty easily, and we're actually going to make a little device that's going to help us measure an angle, and we're actually going to go out and use it for a second in a real life kind of situation. Okay, we'll watch the time and see what happens. But so they can be really, really simple to the point where you can actually make one in about 5 minutes. And they can be really, really complex if like you want pretty exact angles and it's kind of part of your job to do that. Okay, for right now we're just going to trust that the measurement was made in a rather accurate way if we're going to the 10th place, and it ended up being 78.3 degrees. Okay, so the question is, how tall is the Washington Monument? Okay, so you can see they've got it labeled here with a variable y. Hello. Maybe. Come on. There we go. Okay, so they're labeled right there with the y. That's what we're trying to find. That's what this height is. So the question is, how can you use trigonometry to figure that out? And why would tangent be a good choice?
Because you know adjacent.
You know adjacent and you're trying to find opposite, right? So which trig functions deal with adjacent and opposite sides? The tangent and the cotangent, right? Technically that would be a choice too. But since tangent is the one that's a little more common and we're a little more familiar with it, we would generally choose tangent. So how would I write that? The tangent of what? Our angle, the 78.3, has to be equal to what? Y over the 115. So y is our opposite side. That's the one we're trying to find, which is the height of our monument. And 115 is our adjacent side, which is the distance that our surveyor is from the base. So any kind of situation where you have some object that you can assume is probably pretty much perpendicular to the ground, then you can set up situations where you can say, well, that's going to be my right angle then. And so then I can create a right triangle using line of sight and things like that to figure out something that I don't know that would not be easy to just go and, climb to the top of the monument and drop a tape measure down, right? Like, we're not going to do that. So by using the trigonometry, we can find this height without actually having to try to measure the height in some way. We can measure something that's more reasonable, like how far away from the base is he. Okay, so again, back to the calculator. We're taking the tangent. Now, the other thing you can do is just type it, right? Because all of the trig functions are pre-programmed into your calculator. And so you'll notice that when you start typing letters, they're usually italicized. But once you type something that's pre-programmed, it becomes normal type. Okay, so as soon as I hit TAN, since that's something that's pre-programmed in, it became normal type. The thing about typing it yourself, though, is whatever you're taking the sine or cosine or tangent of, you have to make sure you put it in parentheses. So you have to type your own parentheses when you type it yourself, whereas when I come up here to do it, once I hit one of these, the parentheses automatically comes up with it. Okay, that's really the only difference. So my tangent is going to be what? 78.3 degrees. So can I just write 78.3 and I'm good? No, because again, my calculator right now is in radian mode. Now I don't want to really go through the whole hassle of going to the settings, so I'm just going to use the shortcut of overwriting it with my degree symbol. Okay? The pi button that's beside H, it's in there. Okay? So that's the tangent of 78.3. What am I going to have to do to that to solve for y? It's equal to y over 115. So what do I have to do to solve for that y? Exactly. So I'm going to multiply both sides by the 115. And so there's my answer. Where do you think would be a good place to round? What makes sense in the problem? Give me an idea. What do you think? To what? Nearest foot. Does that seem reasonable? Okay, so what is the nearest foot? 555. Could I have rounded to 555.3? Yes, partial feet when we're talking about distance would make sense. So I could have gone to 0.3. But because I'm starting to talk about a rather large number at 555 feet, maybe I would go a 0.3 yet. But going much beyond that, going 0.314, I'm probably not really that precise. Nor would it probably really be necessary to be out to the thousandths place of a foot to get an idea of how tall the Washington Monument is. And so that's something I want you to be thinking about this year, because we are going to do a lot of application problems. That's why the course is named what it's named, Advanced Algebra with Applications. And when we're dealing with applications, when we're dealing with real life, we have to decide what makes sense for our final answer in the context of the problem. So in this context, a 555 would be fine, or possibly a 555.3. It's not necessary to go all the way out to 1.4. We probably aren't really that accurate anyway. But I probably want a little more than just 500. Okay? So in the context of the problem, 555 makes sense. Okay? So, there we go. So a nice little example of how we can use the idea of a right triangle to help us solve something that we can't really measure for ourselves. Okay? Another type of problem similar to that. There we go. We're told that the specifications for a loading dock ramp require a rise of 1 foot for each 3 feet of horizontal length. In the figure, find the lengths of B and C and find the measure of angle theta. So the only piece we're really being given here is the fact that this distance right here from the flat ground to the highest point of our ramp ended up being 4 feet. And we're being asked to figure out what is the horizontal distance, what is the actual length of the ramp itself, and what is this angle. So can you figure out any one of those based on our 4-foot height right here? Can you see that? Yeah. What do you think, Lucy? Okay, and why do you think that one should be 12?
Because you would times 3 by 4 since it's 1 foot for every 3 feet of horizontal.
Okay, so using this information where they say that the specifications require a rise of 1 foot for each 3 feet of horizontal length, the fact that I'm actually going up a rise of 4 feet means I am 4 times as much as what this says. So that means my horizontal length is going to have to be 4 times as much as well. Okay, so the 12 feet for part B we can pretty much come up with just from the information we're given. All right, what should I try to find next? Sorry? The C? How can I find C? Okay, so that means I'm going to take 4 squared plus 12 squared. What's that going to give me? Okay. So what is C? Can that be simplified? If I take 40 times 40, will it give me 160? Say again?
Root 160.
Root 160. Yeah, that's what we're talking about. And I'm asking, can that be simplified?
Yes.
4 times.
4 times what? 4 root 10. Okay. So square root of 160, which would be 4 root 10. Okay, so someone shows up pushing their grandma in a wheelchair, and you're standing by this ramp and they say, "Oh man, a ramp. Excuse me, can you tell me how far up this ramp that I have to push grandma?" And you say, "I do. It's 4 root 10. What do you suppose they're going to do? Who are you? Right? Like, that means nothing to most people. It means something to us because we're brilliant. But, like, most people are going to go, "I have no idea what that means." So again, in the context of an application problem like this, I'm not as interested in exact answers because exact answers oftentimes don't tell us anything. So if you really want to know how long the ramp is, what do we need to do? Put it in a calculator. Which means I don't even care if you simplify first. You can just put the root 160 in. And it's what? Okay, so root 160. Okay, well, we were right on the exact answer anyway. There's our approximate answer. And that's the one that's going to make more sense. If you turn to this person pushing their grandma and say, oh, it's about, what did we say, 12.6. So it's about 12.5 feet that you'd have to push grandma up the ramp. Okay, thank you. Like, that makes sense to them. But telling them it's 4 root 10, they're just going to be like, are you smoking something or what? Like, what are you talking about? Now, one of the things I would ask you to do with applications is if you are rounding some sort of decimal, that you show that with the approximately equal to sign. That way anyone else who looks at your work and looks at your answers knows that this was something you rounded off. It was not something that you got exactly from your calculations in the first place. Okay? And so what I would like to see as I correct your tests and as we go through all these different problems is anything you're going to round off, show that you're rounding it just with that little approximately equal to sign. And so we'll make that a 12.6. And again, just to do kind of a quick check, would that make sense with my other legs that 12.6 would be that? It should, because that's the hypotenuse and it's supposed to be the longest side. It's just barely longer than B, but it is longer than B, so it makes sense. But now what about theta? How am I going to figure out what kind of an angle this ramp is at to get these kinds of dimensions? Any idea what I could set up using that theta that's going to help me solve for something? Okay, I did tangent theta. How's that help? Okay, so we want an equation, right? Because we want to solve something, so we got to have an equation. So if we decide to go with tangent of theta, that's going to be equal to 4 over 12, which is 1/3, okay? But then how do I actually find out what theta is? How am I going to figure out what the actual theta is? Right? This is what I'm trying to solve for now. How am I going to get that isolated? Yeah, there is. Good. So, just like any other operation, we have inverse operations that will undo it. So if we have adding, we have the inverse operation of subtracting to undo it. If we have dividing, we have the inverse operation of multiplying to undo that. If we have squaring, we have the inverse operation of square rooting to undo it. Well, if we have all these trig functions, we have inverse trig functions to undo them. Okay? And so basically that's what we're trying to figure out. How do I undo tangent so that in a sense the tangent is canceled out over here to just leave me with theta, and then over here I'm going to get some answer. And so on a calculator, which is all we're going to be concerned about at the moment, I go to my trig button again, and now what I'm interested in is this second row. All of these that have the little negative ones, okay, that's kind of like the inverse we were talking about with functions just a few days ago. When I say f of -1, I mean inverse function. Well, these sine to the -1, tangent to the -1, these are all inverse trig functions. So I pick the inverse tangent. I put in my 1/3, and I hit enter. Don't you love how helpful your calculator is? So again, I got to go Control Enter. So does that make sense? 0.32? So what kind of an answer is 0.32? Radians. Remember, I was in radian mode. So as a radian angle, the 0.32 would make sense. But we're not talking about radians yet, and usually in application kinds of things, it's degrees that we generally talk about. So I'm going to go back here. I'm going to redo my settings. Go back to degrees. Hit the default. Yes. Go back to calculate. And try one more time. All right, so do it again. Inverse tangent. Oh, come on, catch up already. Hello, there we go. 1/3. Hit enter this time. Hit my Control Enter for an approximate, and now I get the 18.4, which makes a little more sense. So as a degree angle, my theta would be about 18.4 degrees. Okay? So you might see an occasional problem here or there for right now that'll ask you a problem like this where you have to find the angle measure. Again, make sure your calculator is in the correct mode for that. And then you'll just use that second row of trig functions, which are the inverse trig functions, to undo the trig and get to just that theta. Okay, and you do that to whatever it's equal to on the other side, and you should get your answer. Okay. So here's what I want to do. We got 1, 2, 3, 4, 5, 6, 7, 8. Half an hour. Yeah, let's do this. So I would like you to work in 3 different groups. So if we could go 2 groups of 3 and then a group of 2. And each group is going to take one of these baskets. Inside the basket are the directions for making what's called a clinometer. A clinometer is the device that you use to measure angles. Okay? Whether it's as simple as our little homemade arts and crafts version that we're going to do, or really complicated and really exact and something more professional, it's called a clinometer. Now, the way that you do this with what we're going to do, follow the directions. It's very clearly set out here what you're going to do. You have a little protractor thing that you need to cut out. You have an index card that you're going to put it on. You do not have glue. I didn't put that in. I think I have some over there that actually works. So I'll get the glue out for you. When it comes to attaching the straw, though, you're going to want tape. So I'll just have the tape dispenser sitting here. When you get to that point, just come up, get a couple pieces, take it back, and tape your straw onto your index card. You've got the scissors here for cutting out your protractor. You've got a piece of string that you're going to need. And then for the paper clip, we're using one of these kinds of clips. So you just need to kind of thread this through. The purpose of the paper clip is just to add a little bit of weight, because what you're going to end up with is something that looks like this. So that then when you take the straw and you have this whole mechanism attached to your straw, you're going to look through the straw at what you want. And then when you raise it up to look at something else, your string will move, and the paper clip is just there to give it a little weight so that it will actually move like you want it to. And when it will move along that little protractor thing, and then you can read the angle that you've just done by changing your line of sight. Okay? So you're going to make one of these first, try to do it fairly quickly, but follow the directions and do it correctly. And then once your group is done making it, I'm going to give your group a task of something to go figure out how high it is. It's going to be a wall somewhere, and it's just somewhere on this floor. So that means you have to figure out what thing can you measure in order to figure out the height of the wall that I give you to measure. So in other words, you can't actually climb up on anything and measure it. You have to measure something else, use your clinometer to get an angle, and then try to figure out the height of the wall using trigonometry. Make sense? So you need to create your clinometer first. Then when you've got that, bring it to me. I'll take a look at it to make sure that it's all correct and it's going to work. And then I'll tell you what wall I want you to go try to figure out. For measuring what you can measure, you've got a couple of options. Back there in the corner behind Lucy, there's a thing called a, oh now I'm going to forget what it's called. But it's one of those rolling measurers. So if you think you're measuring a long distance, you may want to use that. Otherwise, probably you don't need something quite that long. So we also have tape measures up here. You can go with one of these, which is kind of like what they use out in the field to measure distances, or I've got shorter ones if you don't have very far to measure. So you can pick up one of these to help you measure what you need to. Okay? All right, so 2 groups of 2, 1 group of 3, divide yourselves up, and then come get a basket.
Before you said 2 groups of 3 and 1 group of 2.
Oh yeah, I'm sorry. 2 groups of 3, 1 group of 2. Yeah. This class has 8. The other class has 7. 2 groups of 3, 1 group of 2.
Maybe not the 3 groups.
And glue.
One of the days.
Glue. Here's the tape for attaching your straw when you're ready.